Homework 10, Section 5.3, Independent Events and the Multiplication Rule. In the previous series of videos, we talked about mutually exclusive events and the addition rule. Those probabilities were basically of the form the probability of this or that happening. This section will talk about the multiplication rule, which addresses probabilities of this and that happening. Again, the distinction between this section and the previous section. In the previous section, we did or probabilities and used the addition rule. In this section, we'll be doing and probabilities and using the multiplication rule. But before we can get to that, we need to discuss what are called independent events. And before we get to that, we need to discuss something called conditional probability. Conditional probability is the probability that an event will occur, assuming another event must or will occur. In other words, some pre-existing condition prior to calculating the probability of an event, hence the name conditional probability. To illustrate the difference between a conditional probability and a non-conditional probability, which is also called a marginal probability, let's go back to this contingency table that we saw in the previous section about people voting for a proposition, and they were categorized by two characteristics: their gender, and whether they favored the proposition, they opposed it, or they had no opinion. Just to get us back into speed, 372 males favored, 262 opposed, 87 had no opinion, a total of 721 males. Of the females, 151 favored, 103 opposed, 25 had no opinion, for a total of 279 females, and a grand total of 1,000 people. Also, we have the totals for the numbers who favored, opposed, and no opinion. 523 favored the proposition, 365 had opposed it, 112 had no opinion, and again, for a grand total of 1,000 people. To the side, I have a couple of probabilities, one of which I believe we've already calculated. For example, what's the probability that somebody out of these 1,000 people is a male? Well, this is pretty easy. It'd be easier with a marker that wrote. So let's try this one. Out of the 1,000 total people, how many males are there? 721. So 721 males out of 1,000 total people, as a decimal, would be 0.721. But what's up with this other one? And what's this vertical line here? This is an example of what's called a conditional probability. A conditional probability is still asking you the probability of an event. In this case, the probability that somebody is male. But now we're going to impose a condition. This vertical line is red, assuming that. So you would read this entire problem. What is the probability that someone is male, assuming that, or given that, they favor the proposition. So we're going to answer the same question. What's the probability that somebody is male? Except now we're not looking at everybody. We're only looking at the people who said they favor. This is the condition. If somebody favored the proposition, what is the probability that they were male? Well, we're still going to form a ratio, but when you impose a condition on a probability, you're basically saying, don't look at everybody. Only look at some of them. In terms of sample spaces, what a condition does is limit your sample space. Let's only look at the people who said, we favor this proposition. So in other words, let's stand here and cover up the rest of the table and only focus on the first column. Now, under the condition that they said favor, what's the probability that somebody was male? Well, how many people favored the proposition? And out of those, how many were male? 523 who favor the proposition, 372 of them are male. So we're only focusing on this column because we're working under the assumption that they already said we favor this proposition. How would it look over here? Well, the condition basically dictates your denominator. So out of the 523 who favor, now be careful. The thing to the left side of the vertical line does not tell you what goes in the numerator. We're not going to put 721 here for a couple of reasons. Number one, we're not looking at all the males. We're only looking at the males who favor the proposition. And number two, putting 721 here would give us a probability that's greater than 1, and probabilities can't be greater than 1. So what number does go in the numerator? 372. 372 males who favor. So you could think of the two halves of the conditional probability as the event that I want to happen and the event that has already happened. The numerator has to represent the people in the sample space who fall under both categories, males and favor. Whereas the denominator only has to represent the total in the condition, in this case 523 who favor. Now, I don't know what this decimal equals, but I'm going to take a wild guess and say that it's different than the one that we got before. So out the calculator, and let's see what we get. 372 divided by 523. 0.711. It was close. Actually a lot closer than I thought it was going to be, but it wasn't the same. You'll see why that's important when we define a conditional probability. Excuse me, when we define independent events. Before we abandon this, I want to show you one more probability, conditional probability, and it's going to look like the one that we just did. Let's get rid of part A, and we'll replace it with part C, which is the probability that somebody favors the proposition given that they're male. Now you'll notice it's the exact same two events that were in this conditional probability. Probability that they're male given that they favored the proposition. But now we reversed who's the condition and who's the event that we're finding the probability for. In this case, this would be the probability that they favor, probability that they favor, assuming they are male. Almost as if we were going to go back to this contingency table and say, hey, let's look at the men only, because we're working under the condition that they're male. So where would that put us in this contingency table? Well, the males are here. So if we just said, let's look at the males only for a moment, the condition that you're male, out of the males, what's the probability that they favored the proposition? Well, it's still 372, but now it's out of 721, because we're working under the condition that you're male. So, out of the 721 males, there were still 372 males who favored. And 372 divided by 721 is a number. I think it's less than 50%. 372 divided by 523. I take that back. It's, wrong one. 372 divided by 721 is, it's a little bit more than 50%. 0.516. So I wanted to do the conditional probability in both orders, the probability that they're male given that or assuming that they favor the proposition, as opposed to the probability that they favor the proposition given that or assuming that they're male, to show you that it does matter what order you do a conditional probability in. In the next video, we'll formally define a conditional probability.